Hi. Section 4.1, extreme values of functions on closed intervals. In this section, we'll study methods for finding extrema, maximum and minimum. Let's begin with this definition. Okay, f is defined on a domain D. Then we say f has absolute maximum at a point C if f of c is larger than or equal to every other function value, fx is larger than or equal to every other values, then we say it is absolute maximum. Sometimes this absolute maximum is called global maximum. The same way, once at point C, the value f of c is smaller than or equal to f of x, which means smaller than all other values, then we say that is absolute minimum or global minimum. Now here, and here now f of c is local maximum, which means that locally largest, so that in a small local open interval containing c, f of c is larger than every other values locally, then it's called local maximum. The other way, f of c is smaller than or equal to other values locally, then we say that is a local minimum. Okay, for absolute maximum and absolute minimum, we may say global maximum and global minimum. So rather than absolute here, sometimes people are using global. Okay, now for local here, sometimes we are using relative. Okay, so the relative maximum, relative minimum, or local maximum, local minimum. Let's see this figure. Okay, now that is f of e is local minimum, and also because it's locally smallest value. And now f of c is a local maximum, and f of d is also local maximum. It's locally largest. Here, f of a is locally minimum. Now, in this case, now only we are considering a part of the domain, so that anyway, f of a is the smallest locally, and over there also f of b is the smallest value, so it is a local minimum. Now, if we consider absolute maximum minimum, then the value f of d, that's in y direction, the height is f of d, the value is apparently largest, so that the value is absolute maximum. Now here, f of a seems smallest value and over the whole domain, so that f of a is absolute minimum. Okay. Okay. Here we want to determine the absolute extreme values. For left-hand side here, okay, the function y equal fx is defined on a closed interval, so that at boundary, at end points, here the values are given. So here at c, that is absolute maximum. So here now there is f of c, that is, the value is absolute maximum value. Now here this value, f of b, is the smallest value for all the values, and over the range of the function, this is the smallest value, so that is absolute minimum. Now how about the right side? Absolute maximum is quite clearly we have here. F of c is the absolute maximum. Now here, and this y equal fx, fx is defined in open interval and endpoints are not considered, so that there's no minimum value. And we have a limit, we can find a limit, however, function itself has no minimum value, so that there's no absolute minimum value for this definition. So here, in theory, when we are considering extreme value theorem, we consider the continuous function defined on only closed interval and defined including endpoints. Then here now, absolute maximum value, f has absolute maximum value capital M and absolute minimum value little m, and that means that there is 2 point x1, x2 such that f at x1 is now here minimum value, absolute minimum value, and fx2 is here the absolute maximum value, so that every other value range here that is between small m and capital M. So eventually here now m to capital M, m to capital M will be the range. Okay, so there are the point in x in AB such that the function value will be m at a point, and at another point the function value will be m. Okay, let's see this example, the figures. Okay, for this function y equal fx, now here at x1 the minimum value and x2 the maximum value. So maximum and minimum are at interior points, and sometimes maximum and minimum can happen at end points. At A the maximum value, at B the minimum value, and sometimes maximum at an interior point and here minimum at an end point. And now the other way, the minimum at an interior point and maximum at an end point, so that the maximum and minimum can happen interior or at end points. Okay. Now we'll try to consider how to find extrema. So we'll begin with this theorem that's called first derivative theorem for local extreme values. Okay, and f has local maximum or minimum at a point C, and f prime is defined as C, which means that it's differentiable at the point. Then here f prime at C equals 0. That means that is extrema. Extrema is happen, then now that is f prime equals 0. And it's the extrema is a local extreme, so that locally smallest or locally largest, then now once it is differentiable, then at the point the slope must be 0. For instance, here now in this figure is a local maximum, then now that must be, the slope must be 0. And every over there, of course, over there also, the slope must be 0. And like over there, but that's not differentiable. But once it is differentiable, then the slope at the point must be 0. Okay? So once the extrema happens, then here derivative is 0, but the other direction, the reverse is not true. For example, okay, that is, example is now f is x cubed, then f prime equal 3x squared, and at x equals 0, the value is 0. F prime at 0 is 0, but it's not extrema. Okay, let's see here now the figure. Y equal x cubed. Then at the point, the slope is 0. However, it's not extrema. It's not maximum or minimum, right? So once extrema and differentiable, then derivative is 0. However, the reverse is not true. Okay, we'll define here the critical point. An interior point in the domain of f, where f prime is 0 or undefined, is called critical point. A critical point is an interior point where f prime is 0 or undefined. So from here, now the critical points are that one, and that one, okay? And these are critical points, so the C, E, D are critical points, okay? Let's try to find the critical points for each function. So let's try to find that. Now, okay, f prime, okay, that is, and this is differentiable, so that now, and if derivative is 0, then that is critical points. So that is 12x minus 3x squared. Once we set it 0, then that is now 3x comes out, and 4 minus x, right? Okay, that is 12x minus 3x squared. Okay. Okay, equals 0, which means that now x equals 0 and 4 are critical points. Basically, when you are making graph for the function, then at 0 and 4, the slope will be 0. Also for part B, we start with f prime, that is 4 minus sec squared x. If we say this is 0, then now that is the same as 1 over cosine x squared, so that now here we can say this one is cosine squared x equal 1 over 4, which means that cosine x equal plus minus 1/2. Okay, you can find it and the x quite easily. Start with a circle of radius 1, and cosine is now horizontal, the x component, horizontal component, so that now we are making here, there is a passing half. Of course, the circle is of radius 1 and minus f, yeah. So the angles are that one, okay, this one, and this one, and that one, right? Okay, that is the angle. This one is now pi over 3. Right? Okay, pi over 3, so that this angle will be 2 pi over 3, and you can find the angles. Okay. Okay, here now, for this one, also you can solve it quite easily. And here, f prime, start with f prime, that is x here, minus 3 times 2 over 3, and x to the minus, okay, 1/3, right? So that is same as here now, x minus 2, no, I'm sorry here. Okay, that must be, okay, here that must be 1, right? Okay, not x. Here now that is 1 minus, again 1 minus 2, here x to the minus 1/3, okay. If it is a 0, then x to the minus 1/3 will be, okay, that is now, okay, move this one to the other side and divide by 2, so that is half. So x to the 1/3 is now 2, and x is basically 8. Okay? Okay. Right? There's no mistake. Okay. Now, here we summarize the strategy for finding the absolute extrema of a continuous function defined on here closed interval. Find all critical points in the beginning. So you can find the critical points through derivative. Derivative is 0, or once it is not differentiable, then it is critical point. And then evaluate f at all critical point and end points. And among these values, the largest one will be absolute to maximum, and smallest one will be absolute minimum. Okay, let's try to solve this example. We want to find the absolute maximum and absolute minimum value and give an interval from 0 to 4. Okay, between 0 and 4, it is continuous and differentiable, so that now we can find here the critical point quite easily through derivative. Okay, that is 12 x cubed minus 12 x squared, and here 24x. So that here 12x will come out on x squared minus x. Here that is minus 2. So you can make a separation, x separation 1 and 2, minus and plus. So we can reach at here now 12x and x plus 1 and x minus 2 equals 0, so that we have now x equals 0 and minus 1 and 2. But our domain is between 0 and 4, so that out of there, here the critical points are basically now just interior points. So only the interior points are 2, so that we have x equals 2 is the only critical point. The definition, the critical point is an interior point of the domain of f, so that there's only the critical point. 0 is end points. Anyway, here when we try to find the maximum and minimum, absolute maximum and minimum, we have to evaluate to x is 0 and 2 and 4. This is critical points, and these are end points. Okay, we evaluate the values. F is 0 is same as 1. Okay, now f is 2. Okay, that is, okay, 2, then the first term is 48, and minus and that is 32, and minus 48 plus 1, so that this value is same as minus 31. Now f at 4, well, it'll be large. Okay. Now here, that is 3 times 40 to the 4. That is here. Okay. I believe. Okay, in fact it is 8. Okay, I'm sorry. And then minus of that is 4 to the 3 and 4 to the 4, so that there is 256, and minus 12 times now 16. Okay, we'll write down here 12 times 16 and plus 1. Okay. Now that is okay, we'll try to put out 16 anyway. Then that will be same as 48 minus 16 and minus 12 and plus 1. So we can get here now 16, and this is 20 plus 1, so that is 321. Okay. So among these values, the looks like that is smallest value, and 321 is the largest value. So that is absolute minimum, that is absolute maximum. And for this one, the same way you can do that. Here, just try to find the critical point. So here now, f prime derivative of cosec is the same as minus cosec x times cotangent x. Right? That is a minus of is 1 over sine x. Okay, that is simpler. And times that is now here, there is a sine x on the bottom, and top will be cosine x. If you set it is 0, then here cosine x must be 0. That means that between and here to there, you have to find x. X is now pi over 2, right? Only the value, so that it'll become 0. So we have now the points. So the x-axis and the point is pi over 3, and now pi over 2, and here 2 pi over 3. So you have to find the 3 values, f pi over 3, which is same as, now that is 1 over sine, so that sine pi over 3 is the same as now square root of 3 over 2, so that 2 over square root of 3. Now f of pi over 2, that is here sine pi over 2 will be 1, so it's reciprocal 1. Now f of 2 pi over 3, okay, sine pi over 3, and here 2 pi over 3, the values are the same. Okay, let's look at here the pictorially. And if you are making circle of radius 1, then pi over 3, here now 2 pi over 3, and that is the same height. So the sine is height component, so that eventually you can get here 2 over square root of 3. That's okay. Okay, that's the minimum. Okay, global minimum is 1, and now global maximum is 2 over square root of 3. Okay. Now for that problem again, same way you can do that. The domain is a closed interval, and f of x is given 1 over x plus logarithm x. So f prime, that is same as minus 1 over x squared. And here derivative of natural logarithm of x is 1 over x. Okay, and around here x is non-zero, so that you can multiply x squared on both sides. Then here we have -1 plus x equals 0, so that here we have x equals 1. 1 is between here and there. So to find the absolute maximum and absolute minimum, you have to evaluate here x equal left edge point 1 over e, and x is 1, and now x is 4. These are endpoints, and this is the critical point. So f of 1 over e, which is same as now e and -1. Logarithm 1 over e is -1. Now f of 1, which is same as 1, and logarithm 1 is 0. And f over 4, which is same as 1 over 4, and here plus natural logarithm over 4. Okay. Now looks like this is larger than this one, so that here the 1 is now absolute minimum, and that is now absolute maximum, right? Okay. Okay, this is end of section. Thank you.